So in this video, what I'd like to do is I'd like to actually do some introduction to systems of equations and how it relates to the work of linear algebra. Basically, the work of linear algebra is the solution to systems of equations and how do we characterize those systems of equations, and then how do we really do more expansive work with them. Systems of equations are incredibly powerful and incredibly beneficial basically to the world. As a mathematics, they are the foundation of computers, computer science, they are the foundation of engineering, and their solutions make up some of the most powerful and important results in all of science. Okay. Um, and so, consequently, that's why we have an entire field that's basically about systems of equations, and that is linear algebra. At some point in time, it's going to look like we're not doing systems any longer, but we are. We're going to continue to do systems of equations and talk about them, even though we will be talking about vectors or we'll be talking about linear transformations. At the end of the day, all those things really do help us from a practical standpoint to think about systems of equations. So let's imagine that we have this system of equations. This one is a system with three variables, okay? And this would be z. So let's consider 3x minus 2y plus 4z equals 2, x plus y minus 2z equals 3, and 4x minus y plus 1z equals 1. Now, if I talk about this system of equations, I want to think about how many different solutions I could possibly have. And when we talk about solutions, we're talking about values for x, y, and z that make the system true. That is that allow us to have all three of these equations be true, right? That the left-hand side and the right-hand side end up being actually equal to each other. So 1, there is the possibility that there is no solution. 2, there is one unique solution. 3, there are infinitely many solutions. So those are the three different possible results that we can get from solving the system. What we're going to really look at and ask ourselves is, what does it look like to get one of these solutions, one of the three of them, and to talk a little bit about the third one, in which we might have an infinite number of solutions, but what different ways could we have an infinite number of solutions? So let's talk about first about no solution. When we look at something that has no solution, a system of equations, what we're going to end up with is something that will look like this. We've got 0x plus 0y plus 0z equals 0, 0x plus 0y plus 0z equals 0, 0x plus 0y plus 0z equals 5. Okay? In this case, we often will say something like this. 0 equals 5, which is impossible. So what we've done is we've gone in and we've used some elimination or maybe substitution in order to solve this system. What we've gotten is an impossible result. That is that 0 equals 5, right? So there is no solution. That's our telling statement. Okay? Let's take a look at the second one. The second kind of solution that we might have is one solution. And one solution looks like this. This is the one that we probably think of when we think about the solution to a system of equations. X equals 1, y equals 2, z equals 3. Okay? Clearly defined solution. One solution. Or we could have infinitely many solutions. And in the case of this particular system of equations, what we possibly could have is something like 3x plus 2y equals negative 1, 7x plus 2y minus 3z equals 4. Okay? What we'll notice is that x and y are dependent upon each other. We'll have x be the independent variable, y be the dependent variable. So depending upon what I choose for x, I'll get an infinite number of y's. Or we could actually have two independent variables, x and y, and we'll have a third dependent variable in z, okay? And these two are both examples of infinitely many solutions. We'll talk about them. They're slightly different, okay, in terms of how we characterize or envision what those solutions are. But for the most part, what we want to think about them as is we want to think about them as an infinite number of solutions. So let's talk just for a moment about what this system of equations means geometrically. Okay, so I look at 3x minus 2y plus 4z equals 2, and this is a plane. This is a plane in 3 space. How do we know? We have 3 variables, two of which are going to be dependent, x and y, and z will be our dependent variable. So that's going to be a plane in 3 space. And then I also have another plane in 3 space. And I have a third plane in 3 space. So what we want to do is we want to imagine what would happen with these 3 planes. What are the possibilities in terms of what's going to happen with those 3 planes? All right, and what does a system of equations look like from the perspective of the solutions to its systems of equations? So the first kind of solution that we have here is this no solution kind. And what you want to see here, given my limited drawing ability, is you'll see that we've got 3 planes here. And the idea here for no solution is that the planes are going to be parallel to each other. The way we envision or think about what happens in a system of linear equations with its solution is that the intersection is the solution to the system of equations. In this case, there are no intersections because the 3 planes are in fact parallel, and so consequently, there is no solution, right? No intersection, no solution. And the way that we envision that is that these planes are actually parallel to one another. The second is to think about one solution. In the case of one solution, this is probably the easiest one to think about, we have the planes meeting in one and only one solution, okay, or one and only one point, okay? So the solution for one solution is characterized as a point, right? We say that its solution is called a point. So our next example is infinite number of solutions, but we'll call this one A because we have 2 different examples for infinite solutions. In the first one here, what we get is we actually end up with a line. This is the intersection of the 3 planes, and they'll intersect in a 2-dimensional line. And you can kind of see this is going to end up being the equation of a straight line. Okay, that's a linear equation right there in x and y. And so we want to imagine that would end up being our line. When there are only 2 variables, right, and that's one thing we want to notice here, 2 variables in the solution, that's a line. Now, let's kind of mark what this looks like on the actual page. So we'll highlight that. And you can see right here, this is the intersection of those 3 different planes, okay? And that ends up being the solution to this system of equations. So now, the fourth kind is this infinite number of solutions, but it's a different kind of infinite number of solutions. In this case, rather than the 3 planes meeting in a line, which will give us an infinite number of solutions, we're instead having that the 3 planes are actually all the same plane, right? And if they're all the same plane, what we can see right here is that we're going to get an equation in 3 variables, like 7x plus 2y minus 3z equals 4. That's the equation for a plane, okay? So the equation's in 3 variables. And that's the equation for a plane, and that's another kind of infinite number of solutions. There's an infinite number of points on that plane that actually will solve the system of equations. So those are our 3 kinds. On the one hand, we have the one solution, or no solution, excuse me, in which the 3 planes don't meet at all. 2, we have one solution where the 3 planes meet in a point. 3, we'll have infinitely many solutions, and we have 2 different choices for that one. We're either going to have that the plane meets, or the 3 planes meet in a line, or we have that the 3 planes are actually the same plane, and so consequently their solution is another plane. Okay, and that's one way to, those are 4 different ways of actually visualizing the solution to a system. Let's kind of characterize them. So let's characterize the algebraic solution, and then we'll characterize the geometric solution to go along with it. So first, for the algebraic solution of no solution, what we have is we have no intersection. And that's our geometric solution. Basically, we have parallel, or what we call skew, planes. Skew planes are planes that are necessarily, they do not touch, but they are also not necessarily parallel. When you have, say for example, if you have more than 3 dimensions, you can have skew planes, or skew volumes actually, that never meet but are also not technically, they don't technically have the same slope. So essentially what we have here is we have no intersection. One solution, we're going to characterize as a point. And then when we have an infinite number of solutions, we're going to characterize these geometrically depending upon how many variables that we have. Now, in the case of each variable, I want you to think about in terms of we're going to have a dependent variable, and we'll have one or more independent variables. So like, for example, if we're in two variables, we'll let y be our dependent variable and x be our independent one, and we know that that's going to be a line, okay? If we're going to have three variables, okay, we'll end up with a plane. A plane is flat, right? Okay, it's actually two-dimensional, all right? It's a two-dimensional surface, okay? And that's in reference to the number of independent variables. Line being one-dimensional, because it's got one independent variable. Then, if we have four variables, one of them will be dependent, we'll let z be dependent, and then we have three dimensions, so we call that a volume. A volume has three dimensions. And then if we go with five or more variables, say for example, this fifth variable will be the dependent one, and what we end up with in 4 dimensions, and this is something pretty much that's impossible to kind of like visualize from a geometric perspective, but this thing here is called the hypervolume. And that's something that's in 4 or more dimensions. So depending upon how many variables that there are inside of our geometric solution, that actually changes what we call the infinite number of solutions ones. So if we have one independent variable, say n and x, that's a line. Two independent variables, x and y, that's going to be a plane. If we have three independent variables, like our w, x, and y here, we're going to have a volume. And then if we have five or more independent variables, we call that a hypervolume. Okay, and so consequently, we're going to think about the solution to systems somewhat inside of this particular way of thinking about this geometrically. Now, there are going to be other geometric ways of thinking about the solution to systems, and we'll talk about those in more depth, especially as we get more and more into Chapter 4. So now what I want to do is I actually want to relate systems of equations to vector equations. And in particular, what we're going to do is we're going to start out with some notation, and then we're going to show how that notation and the use of matrix algebra will actually tie systems of equations to vector equations, and will allow us to allow us to deeply expand what we're going to be able to do with systems of equations. Systems of equations from a solving perspective can sometimes be really cumbersome and really burdensome, and that's especially as we get past 3 dimensions. Right? It can get really difficult to use elimination or substitution when we have really large systems, right? Where we've got to like push around a lot of variables. It can get really confusing and really messy. So what we want to do is we want to get a form that'll actually make this a lot easier. And that form that we're going to be using is this vector equation. And then we're going to be stripping things off of the vector equation in order to make that even more simple to look at and simple to use. So let's consider this system right here, okay? And what we have is it's a system in 3 variables. So we've got 3 equations, okay? And on the one hand side, we've got a set of coefficients being multiplied by our variables. And on the left hand side, we might have the constant values for the system, okay? Now what I'm going to do, and I'm going to pose, and then we're going to, in just a moment, we're going to show that in fact the two are equivalent. I'm going to have that the vector equation is going to be made up of what we call a coefficient matrix. And this coefficient matrix is going to be made up of the coefficients inside of the system. So this is going to be 3, -2, 4. So you'll notice this is the x variables, this will be the y variables, and this will be the z variables. Okay? X, y, and z. Now we have 4, 1, 0, 3, -1, 2. And what I'm going to posit, I'm going to claim, is that when I multiply this by the vector x, y, z, okay, and I set it equal to 2, 1, 4, what I'm going to get is I'm actually going to get a completely equivalent system. That actually, if I do this multiplication, like I've been doing with matrix multiplication, what I'm going to get is I'm going to actually get this very same system of equations. Okay, so let's see. Remember that when we multiply matrices, we're going to multiply rows by columns, right? We'll use dot products for rows by columns. So this is going to be 3 times x minus 2 times y plus 4 times z equals 2. That's the first line. And so basically that's going to be this thing here set up equal to the right-hand side. Then we'll take 4x plus y plus 0z will equal 1. And that's that second product. And then 3x minus y plus 2z will equal 4. And what we can see is that these two are in fact identical. Okay, those are identical systems. All right. So what we want to get here is that if we take this matrix, a matrix made up of the coefficients, okay, of the system of equations, we multiply it by a matrix made up of the variables, okay, that what we'll end up getting is we'll end up getting the right-hand variable, which will be made up of these values on the right-hand side of the system of equations. Okay, so let's talk a little bit about some notation and some definitions. This thing here, okay, we'll call it A, right? A is called the coefficient matrix. It's made up of coefficients from the system of equations. This vector here, we're going to call it x. Okay? We'll get x. And x, we're going to call x the vector of unknowns. We're also going to call it soon, it'll end up being called the solution vector. Or vectors. Because what it'll end up giving us is the solution to the system of equations if there actually is one. And then this third one here, we're going to call it B, okay? And we'll call that the right-hand side vector. Most of the time, we're not going to call it the right-hand side vector. Most of the time, we're going to call it B. If I make reference to B as a vector, I'm talking about the right-hand side vector. Just like if I use the term x, what I'm talking about is the vector of unknowns, the vector of our variables x's. And A is generally going to be thought of as our coefficient matrix. Okay? So what we end up with is one of the most powerful sets of symbols inside of this entire class. That is AX equals B. This thing here is called a vector equation. And it is another way of writing a system of equations, right? We have a coefficient matrix, A, times a vector of unknowns, equal to some other vector. And what we'll see is that this x value is going to end up being the solution to our system of equations. So let's consider the system 2x minus y equals 1 and 2x minus 2y equals 3. So now what we want to do, if you just take a minute, pause the video, and go ahead and solve that system of equations. Use elimination, use substitution, shouldn't take you very long. So once you solve that, what you're going to see is that you're going to end up with x is going to equal negative 1/2, and y will end up equaling negative 2. So that's the solution to our system of equations, which we know is going to end up being a point now. So let's see what happens when we actually write our vector equation. So now I have 2, negative 1, 2, negative 2. And those are the coefficients. They give me my coefficient matrix. And I'm going to multiply that by xy. But instead of xy, I'm actually going to put in my values here for my x and y that I've got as the solution to the system. All right, there's our vector of unknowns, but now it's going to be thought of as a solution vector. That is it's the solution to the system. And what we want to see is that going to end up giving me 1, 3, right? And that'll in fact show me that in fact this is the solution. So 2 times negative 1/2 is going to be negative 1 plus 2, okay, and that equals positive 1. So that's good. That's exactly what we're looking for. Next, let's take 2 times negative 2, that's going to be negative 1, plus 4, so negative 1 plus 4, that's going to end up giving me 3. And what I see here is that this vector, solution vector, in fact does solve the system, right? And we can see how, and using matrix multiplication, we can actually prove that it in fact is the solution vector. All we've got to do is take the coefficient matrix, right? This one here, A, multiply it by this solution vector, negative 1/2, negative 2, and that'll end up giving me B. And that's how, in fact, I know that that is, in fact, the solution vector. Okay? Let's take a look at it again, another. So let's consider this system. In this system, my coefficient matrix is going to be 3, negative 2, 3, 4, negative 4, 7, 2, negative 2, 0, and I'll multiply that by whatever my solution vector is going to end up being. Now, if you think about this one for just a moment, all three of these equations are set equal to 0. We got a 0, a 0, and a 0. And so if you think about it, one solution is definitely going to end up being, and we'll call this x, our vector of unknowns, definitely we're going to end up with 0, 0, 0. Okay? And if you think about it for a second, you'll figure out why. But let's go out and check it. 0, 0, 0. Okay. So 3 times 0 is 0. There's that. Negative 2 times 0 is 0. 3 times 0 is 0. So add those all together, we get 0. 4 times 0 is 0. Negative 4 times 0 is 0. 7 times 0 is 0. So again, we end up with 0. 2 times 0 is 0. Negative 2 times 0 is 0. 0 times 0 is 0. So when we add all those together, we end up with 0. So what we see here is x equals 0 is a solution to the vector equation and to the system of equations. Okay, this actually introduces for us a very special term that we're going to see a lot of, and we saw a little bit of it when we talked about differential equations, but this is the idea, this thing here is called a homogeneous system. A homogeneous system is one in which B, our right-hand side vector, is equal to 0. So that is the system is set to equal to 0. Is set equal to 0 for all equations. So basically what we have is we have no constant term, right? And if you think about this geometrically, this means that each plane goes through the origin. We'll be talking a bit about these homogeneous equations because they end up being very, very special and very, very important. And what you'll see, though, is you'll see that with a homogeneous equation, we're always going to have at least this solution, x equals 0, 0, 0, or however many zeros that you're going to have. And that's because if you plug in 0 into each one of these variables, you're always going to have at least that solution. The question is going to be whether or not that's the only solution to what we call ax equals 0, okay? And we're going to write that out. That's going to be our vector equation. Ax equals 0, okay, is homogeneous. Is a homogeneous system. Ax equals b, where b does not equal the 0 vector, is non-homogeneous. And those end up being our big definitions from the standpoint of how do we characterize different systems. 1, ax equals 0 is homogeneous. Ax equals b is non-homogeneous. Great. The last little piece that we want to get into here, and the last piece of notation, is called an augmented matrix. And the idea of an augmented matrix is to simplify even further the notation for vector equations. So let's say, for example, we've got 2, negative 2, 3, 0, and we'll multiply that by an x1, x2 vector, and that equals, call it 4, negative 1. 4, negative 1. And what we're going to do with an augmented matrix is we're actually going to eliminate the x1, x2. We're going to pretend like it's there, but it's not really going to be there. It's going to actually shorten our work time. And this is going to be really important if you're throwing things into matrices. All right, so now what we'll get is our augmented matrix is going to be the coefficient matrix with this like kind of line down through the middle, and our right-hand side vector put together. And what's implied here, so here's A, here's B, the vector, and there's an implied x vector. It's just not stated. There's an implied x vector, or implied vector of unknowns. So like, for example, if I said 3x, right, minus 2y plus 4z equals 2, 4x minus 7y plus 3z equals 1, 3x plus 2y minus 4z equals 0. I can rewrite this as an augmented matrix, and we're going to see that it's going to come in very handy when solving. I'll get 3, negative 2, 4, and then I'll have that little dashed line 2, 4, negative 7, 3, 1, 3, 2, negative 4, 0. Okay, and that ends up being my augmented matrix that's equivalent to the system. So you can see we can write as vector equations, we can write as a system of equations, or we can write these things as augmented matrices. And it's just up to us as to how we want to go about writing them. All right, so that completes our introduction to systems of equations. What we want to do here is we want to think about, okay, what are the different ways that I can actually write a system of equations, and discuss, the number of solutions and what those solutions are when we characterize them geometrically. So basically, those are the big things that we've gotten inside of this particular lecture. All right, this ends the lecture.